Section 10.7, Taylor polynomials. In this video, I will just introduce the formula for the Taylor series or Taylor polynomials. Let's recall really quickly how important it is to have the power series expansion for a certain function. We did learn the power series expansion, for instance, for this beautiful rational function, 1 over 1 minus x, and we know that this is the formula. We know where this comes from. We also was able to find, for instance, the power series expansion for arctangent of x. Yeah, we remember this. However, what we will need sometimes to have the power series expansion. Basically, we would like to represent a function as a polynomial of infinite degree. And for instance, this is the list of nice functions: sine of x, cosine of x, e to the x, natural log of 1 minus x, or many other functions. And why we will even think that we need this. These are relatively simple functions, but they cannot be evaluated for like most of the values from the domain. We can evaluate really quickly for the relatively few values. Yeah, we know sine of pi over 6. We know, for instance, sine of pi over 3, pi over 4, some values from the unit circle. But what is sine of pi over 13, for instance? Yeah, we will be not able to do this. I mean, we can try, but we will definitely need some tool for the numerical approximation. But when we will try to get the representation, the approximation of the polynomials with infinitely many terms, of infinite degree, we can easily evaluate these functions for almost any number from the domain. And that means we would like to have the power series expansion for these functions. Also, I list a couple of functions which are a little bit more challenged. And for instance, we cannot integrate these functions. You may think, you may look at this, that means now, we still like to see the integral, and if the function is approximated or if the function is rewrite as a power series, we can easily integrate a power function. We also know how easy it is. That means this is just the quick review how important power series expansion for almost any function, if it is possible to do it, of course, because we need to have the nice function, which nice function means analytic function. But we will talk about these details later. In general, we need the power series expansion to deal with some mathematical tasks. Okay, that means let's see. These two, we get the power series expansion based on the geometric. Based on this one, which actually the first one is almost a tool. And then by manipulating, by differentiating, integrating, we did get, for instance, arctangent. You remember from the previous videos, the formula. But not, for instance, these functions, we cannot really take 1 over 1 minus x and differentiate or integrate, because we will never relate to sine of x, cosine of x, or any other functions. That we need additional tool. And to get the power series expansion, because power series expansion, let me take the general formula. Yes, it's basically c sub n x minus a, the center, to the power of n. That means that's what I mean. This will be, and we would like to have the formula for sine of x, for cosine of x, and so on. That's what we will try to do. In order to look at this more globally, more general, this coefficient, we will try to relate to a function. Because if we will get the formula for the coefficient C sub n, which is connected to the particular function, then we can have this formula and respectively power series expansion. X minus a to the power of n, it's part of the formula, but always stays the same. Yeah? So we can see for this one, we have the coefficient C sub n equals to 1. For this one, the coefficient C sub n is negative 1 to the n over 2n plus 1. And this is that variable, that power 4. Yeah? X, of course, minus 0, centered 0, centered 0. Okay, that's me. Let's try to get the general formula because that's the point of this video. I have a couple of notes, but we already said how important it is because it's an extremely useful approximating tool. We can get the values, we can get some functions, and we will definitely start talking about the Taylor polynomials. Okay, and then we will extend to the Taylor series. But first of all, let's actually even check why we even call Taylor. Taylor polynomial or Taylor series is the power series, but why we call Taylor? Okay, let's start. As I mentioned, this is the general formula for the power series, C sub n x minus a to the power of n, and that's the expanded form. C sub 0, C sub 1, C sub 2, and respectively the powers of x. And now, the coefficient C sub n, we will try to rewrite in terms of a function. That's first of all, what I did substitute instead of x the center a. That's when we substitute to the f of x in the formula, general formula of the power series, that's the expanded form. If I substitute instead of x a minus a 0, 0, 0, 0, we will only end up with C sub 0, the first term. Okay, that means this is at least some connection. C sub 0 is always f of a. Yeah, really good, really good. But let's keep working. Okay, now, okay, that means this is the power series expansion, general form. And if x is a, it will be C sub 0. Now, I will take this power series expansion and I will differentiate. Derivative of C sub 0 of the constant is 0, gone. Derivative of C sub 1 x is C sub 1. Derivative of C sub 2 x squared, theoretically x squared, is 2x C sub 2. And I carry negative subtracting a, but that's the same. Yes, the same thing, because inner function has derivative 1. Derivative of x cubed will be 3x squared. Derivative of x to the power of 4 is 4x to the power of 3, and all of the constant are copied, and so on. Okay, that's a derivative. You know how to differentiate. You can maybe pause the video and check that you feel confident with that line. Okay, and we will do the same. Instead of x, we will put a. Then if x is a, this is gone, this is gone. All of the terms are gone, only the first constant term stays. Okay, that's when we can see we have another connection. C sub 1, it's equal to the first derivative at a. Let's find the second derivative. The same thing. We will differentiate each term. Derivative of the constant is 0. Derivative of x is just the constant, 2c sub 2. And then the derivative of x squared will be 2x and copy that constant. Derivative of x cubed will be 3x squared and copy 4c sub 4 and so on. And the same thing. We will replace x with a. Gone, gone, and gone. This means if the second derivative at a is equal to 2 times c sub 2, but I'm just trying to keep that 1 because you probably guess what I'm doing. I'm trying to find the pattern. Function at a is c sub 0. First derivative at A, it's 1 times C sub 1. Second derivative at A, it's 1 times 2 C sub 2. Let's just do the third derivative. I just differentiate that power function. I am replacing x with A, and all of the terms will be gone except the first one. 2 times 3 C sub 3, and I'm keeping 1. And so we can easily see the pattern. C sub 0, first derivative 1 C sub 1, second derivative 1 times 2 C sub 2, third derivative 1 times 2 times 3 C sub 3. Okay, so now if we will think about the fourth derivative, you can probably say aloud it will be 1 times 2 times 3 times 4 C sub 4. And then if we think about nth derivative at A, we can notice the coefficient of C sub n is the factorial corresponding values. 4 factorial, this was 2 factorial, this was actually 3 factorial, 1 factorial, and even 0 factorial. Yes, 0 factorial C sub 0. 0 factorial is flat. Okay, that's what we did manage. This is quite important and quite famous formula. The nth derivative at A equals to n factorial C sub n. Okay, and if we solve this for C sub n, we will get this nth derivative at A over n factorial. Okay, that means this beautiful formula can be placed in the general form of the power series. Let's do this. That means this is the general form. But if I take this general, the coefficient, and substitute this formula that we just developed, we will get this power series. The nth derivative of at A over n factorial, and then the power form x minus a to the power of n. That's the expanded form. And this was developed by one of the mathematicians. Okay, that's Taylor. That's the reason that we actually call Taylor series. Yeah, it's because of the last name of the mathematician. Okay? That when you see this formula, we can still say it's a power series expansion, but to be more specific, we will say Taylor series. And we can see we have 3 dots, meaning that we have infinitely many terms. We, of course, have a couple of conditions because not all of the functions can have power series expansion, power series like representation. We may notice we need the nth derivative. That's when we definitely, one of the conditions is function must be infinitely many times differentiable. Okay? That means the function can be differentiated infinitely many times. That's the condition, because we can see we will keep working. And that means this is one of the conditions, but talking about the Taylor series, we will talk about this. Okay, let's look at this also slide. When we have centered 0, because the previous one, Taylor series, can be centered at A, any number. But when we have center actually specifically 0, we may say that this is Taylor series centered at 0, and this will look like this, 0, then we don't have to subtract that 0. It will be just x to the power of 1, x squared, x cubed. And this is also quite frequently seen. And this is called Maclaurin series. Okay? That means the special case of a Taylor series is actually Maclaurin series, but we can still say. And yes, the Taylor series is named after English mathematician Brooke Taylor. Maclaurin series is named from the Scottish mathematician Colin Maclaurin. Yeah? But they worked independently, and Maclaurin is just a specific case of a Taylor because it's just centered at 0. Any power series representation centered at 0, we can call Maclaurin series, even from the previous section. Okay. Or we can also say Taylor center at 0. Okay, and let's just say, because this video was just focusing on this formula. Okay, on this formula, I mean centered at A. That's the coefficient C sub n defined this way. And let me just show you this slide, and I will stop, because the other videos, the other session will talk about more details. But now let's look at this. Yeah, in general, function is the sum of a Taylor series if, and this is function, this is the formula that we just learned. And what we can do, we can split this for T sub n of n plus R sub n of n. That means T sub n, it's just the terms from 0 to n, which we can call is the partial sum. We remember partial sum. But since we're talking about the Taylor series, this will be the nth degree Taylor polynomial of the function. That means this is a Taylor polynomial. And then if we would like to have the entire expansion plus the rest of the terms, remainder, from 0, I is changing from 0 to n. As we can see, this will be finite number of terms, n, partial sum, nth degree Taylor polynomial, plus the rest of them. The degree will be n plus 1, and so on. And then we, of course, we have a couple of conditions. That's one of the theorem, the Taylor series converges to f of x. Yeah, that means function can have a Taylor series representation if and only if that term, the remainder, is approaching small numbers, is approaching 0. Yeah? For the big, meaning the derivative are not growing quickly. Derivative, because k, in this case, k, this will be I. It's the degree of it's the derivatives. That means derivatives, they're supposed to be small. Okay? If they're growing like if the derivatives at the center are big, then probably this will be divergent and we will not have power series representation, Taylor series representation for the function. But as I said, we will talk about this later. This video basically covers this formula. That's mean make sure that you know where the formula comes from. Okay? And we will talk about this Taylor polynomial and the other details later. One more time, the formula that we developed is this one. Yeah? C sub n equals to nth derivative at a over n factorial. Yeah? Okay, thank you, and please check the next video. Thank you.